So now let's look at what are the equations for the different types of coordinate frames. So we need to know position, which is r. We need to know velocity, v. And we need to know acceleration. And we've got three types. So Cartesian, this is the x, y, z. So the position vector is going to be r equals x I hat plus y in the j hat plus z in the k hat. Okay, just x, y, z would be the coordinates that you're given for the particle. So then velocity, we take the derivative. R dot is just going to be the time derivative. So we just go x dot I hat plus y dot j hat plus z dot k hat. Acceleration, a equals r double dot, which is just x double dot I hat plus y double dot j hat plus z double dot k hat. So Cartesian's really easy because the x, the y, and the z will change with time, but the I, the j, and the k do not. The direction vectors are static. The position changes, but the direction of that coordinate frame doesn't change. The coordinate frame is fixed. Polar or cylindrical is different. So for a polar or cylindrical system, then the r theta vectors do change. So the position here always points towards the particle. So we'll have r ur plus z in the k hat if it's cylindrical. So focusing here, r, ur, let's look at particles going on a path. So if this starts out, let's say this is initial, 0, and this is final. Actually, that is going to be too big of a swing. Restart that. Okay. So let's say we've got a particle out here. Now, just looking at the two-dimensional, we know that UR points towards the particle. U theta points away from the particle, 90 degrees to UR. So then let's say the system rotates. So the particle is moving on its path. Say the particle moves here. Well, now UR points towards the particle. U theta still points 90 degrees. So you can see that the UR and the U theta directions changed. This angle of rotation, right here, the angle from the start to the end, is theta. And the speed of rotation is theta dot. So if we want to know how much these vectors are changing, we just look at theta dot, which is how fast they're changing, and then we look at what direction they went in. So the UR, we need to know what UR dot is. How does UR change with time? Well, it changes, its speed of rotation is theta dot, the direction is u theta because UR went from its original spot to closer to the where u theta was. Now, u theta dot is also going to rotate with speed of theta dot, but in this case, the u theta vector went away from the UR. You see, it didn't go in that direction, it went in that direction. So negative theta dot UR, because it points away. So for the velocity, we know here, we take derivatives r dot, we've got to use chain rule. So r dot UR plus r UR dot, and then plus the k hat. The z doesn't change. So now you see here, but UR dot is not a unit vector. We have to get it in terms of the unit vectors. So we know that the velocity has to equal r dot UR plus, instead of UR dot, we use what it actually equals, which is theta dot u theta. So plus r theta dot u theta plus the k hat. So whereas the position started out with just two components, one in UR and one in k, the velocity is going to have three components, UR, u theta, and k. Because the UR vector changed, the UR vector is also moving. So now we have to differentiate that, and it gives a u theta component. If it is cylindrical, the z part is included. If it's just polar, just two-dimensional, then you'll have these same exact formulas, but there will be no z on it. So then for acceleration, we take the derivative again. R double dot equals, so looking at this, we'll have to use chain rule and product rule in here. And we use another product rule here. So for this one, we'll have R double dot UR plus R dot UR dot, and then add this one. And this is a triple product rule. So we'll have R dot theta dot u theta plus, we take the derivative of that one. So we'll have R theta double dot u theta plus derivative of this one now, R theta dot u theta dot plus z double dot k hat. So now let's plug in the derivatives for those unit vectors. So here again we have r double dot UR plus r dot theta dot u theta plus r dot theta dot u theta plus r theta double dot u theta plus r dot theta dot, and u theta dot over here is negative theta dot UR, so this will actually become a negative. So we'll have minus r dot, sorry, r does not have a dot. start back over with that one. So r theta dot, and then this is going to be negative theta dot, so that'll square ur plus z double dot k hat. Now this is really long, but we can group similar terms. So r dot equals ur. We'll have r double dot from this one plus or minus r theta dot squared, and then plus u theta times r theta double dot plus, there's two r dot theta dots, so we'll have two r dot theta dot, and then plus z double dot k hat. So this one is the velocity, this one is the acceleration for the polar. Now, these formulas right here that we just worked out, you can keep those and reuse them. So if you want to, when you are working a problem, if r is given, you can start with r and just take all of its derivatives, or you can just use these formulas and plug stuff in. So that will be really helpful to know for the exam. Then finally, we'll have normal tangential. Now for that one, remember that the coordinate frame is fixed on the particle. So we've got the particle moving around. The coordinate frame is on the particle, so the r vector is 0, always. Then the velocity vector is going to be the speed in the tangential direction. So because we know the tangential direction always points in the direction that the particle is moving. So if it points in that direction, then the particle must be moving with that speed. So VUT. Then the acceleration is going to be, UT is not constant because remember the particle's moving. So we'll have A is going to be V dot UT plus V squared over rho UN, where rho and this one is kind of a lengthy formula, so this is why you need to know the path. Rho is equal to 1 plus dy dx squared to the 3/2 over d squared y dx squared for path y equals f of x. So this is why you have to know what the path is. Now, important things to note here. Position vector for normal tangential is always 0. Velocity is always along the path. Acceleration has a component along the path because it could be speeding up or slowing down, and a component normal to the path because it could be turning left or right.